All right, here's some help on number 11 in particular when you're doing the that funny price and quantity demanded function with that inverse. Well, we'll see here in just a second here. It's got some funny things that we briefly talked about in class, but this will give you hopefully a little bit more direct insight into another video that you can watch on there. Leaves a little to be desired, but it's a good video. I just underlined it. I read through this, and this is what I get from it. Quantity demanded x is a product is inversely proportional to the cube of the price. What I wrote in red there, that's how you write an inversely proportional statement. And so that's how that goes. It means write it as a, instead of a product, a quotient. And then when the price is $10 per unit, the quantity demanded is 125. So using that formula, you put those two values in there. Ultimately, what we end up doing for that is that we can solve for that k, and that constant k is the growth constant for this demand function. So what we'll do is keep on a rolling. There's also more information we get, like the cost function there with when you have an initial cost, 120, that's like your y-intercept, and cost per unit, you write as 2 times x, so it's $2 per x units to give you cost. So those are all the things that we're given. Now we need to maximize profit, which means take the derivative of profit and set it equal to 0. We don't even have a profit function, so that's the thing we need to work on is how can we create a profit function? And if you remember, it comes from xp minus c, revenue minus cost. Revenue can be written as x times p, or the number of units demanded times the price. That's a way of doing revenue. That's what we're going to work from here in the next piece. The things are given again, and we are going to basically build our profit function by filling in the xp and c so that we can actually take the derivative of this thing. So that's where we left off on the last page. I just recopied it. Now, let's put in the x, let's put in the cost. The only thing is if I'm going to make this thing work, I need to have a function for p. But if I'm going to put it in there, I don't want to put p in there. I can't really deal with it. I want to put in p in terms of x. Like, is there a way I can write the price as a function of something x and, blah, blah, blah. We need to have it as a function of x. This is the work that we end up doing here. So if we take this thing that we have, well, I told you guys we need to find k in that original function. And so with what we had given, we were going to solve for it. And the way you solve for it is multiply both sides by the denominator, 1,000. So I'm going to circle some of these things so you can see them kind of in live mode. Where's my printer here? This little dude right here, if I want to solve that, multiply both sides by 1,000, and you get k equals 125,000. That's our k. Done deal. So once we have that k, then x is 125,000 over p cubed. Well, that is a function, something that I can solve for p within, and if I can solve for p, that is going to be p equals something with that 125,000 and x. That's what I need to put in here up above for my p function. Okay, so let's keep rolling. So I'm going to write all this in here. We're going to solve for p in that circled equation. First thing you do is the denominators there, that p cubed and that x, well, I can multiply both sides by p cubed and divide by x on both sides, or you can just swap those two. It's kind of a 1-2 deal. Multiply by p cubed on both sides, divide by x. I get what you see at the bottom there, very tiny, p cubed equals 125,000 over x. Then we cube root both sides, and 125,000 is actually a perfect cube. So it's 50 over x cubed, or cube rooted, the cube root of x. So I just split up that cube root of 50, cube root of 125,000 is 50, cube root of the x is cube root of x. I left it. That's our p. That's the thing we needed. We can put it in our function. That little dude there. And you notice I took out the cube root. I put in 1/3 power. You can kind of see why. Do you notice that I have x times 50 over x to the 1/3? I can simplify there because I have x's to various powers. I can simplify. So let's look at that more closely. So okay, here we are. This is where we left off. I can write that as 50x to the 2/3 because this would be x to the first here, and an x to the 1/3 in the denominator. And if you remember, you have same bases, you subtract the exponents. 1 minus 1/3 gives me that 2/3 exponent. Minus 2x because I distribute the negative, and minus 120 because I distribute the negative. And that's it. Okay, so there's our profit function that we're going to take the derivative of. So the whole point is, if you want to maximize or find the optimal profit, you take the derivative, set it equal to 0, and if it's a simple function, the maximum will be a peak, where the derivative is equal to 0. So I'm going to set the derivative equal to 0. So I can find that peak. There's the derivative. 2/3 times 50 is 100 thirds. Take away 1 and get 1, negative 1/3. And then minus 2. That's the thing I have to set equal to 0. And then from there, add 2 to both sides to multiply by the reciprocal on both sides to get rid of that 100 thirds. And here's where I end up. X to the negative 1/3 equals 6 over 100. And if you don't know what to do with this, I want to have x equal something. There's a couple ways we could approach this. I think the simplest one is if you take both sides to the negative 3 power. So if I take each side to the negative 3 power, it creates x to the first on the left, which is what I want, and I get 6 over 100 to the negative third. Honestly, I think that's the easiest way to simplify this. That way I get, remember the operation, the whole idea is to get x to the first power on the left, or by itself, whatever side. In this case, on the left. So that'd be to the power of negative 3 would actually make this, because you multiply these powers right here, that'll multiply and make 1. So that's our goal. X to the first equals, and then I get a decimal 4629.63. I have an option in the calculator to leave it as a fraction. I actually want to use that because it will make it easier. The fraction's a pretty nice number. So here's what we're going to do with that x. That x is when my profit maximizes. At that various production rate, or amount of production, 4,629 units and some change, that's when I maximize profit. Well, if you read the question back in the beginning, it says, what price maximizes profit? Not what number of units corresponds to the maximum profit. It's what price. Well, I have a little function for price. Remember, a little p. This is price. And if I want to know what price maximizes profit, I need to put my units that I have maximizing my profit in here, and then I can have the price that corresponds to the maximum profit. So I put this, I could put in 4629.63 and everything would be just hunky-dory. Or I could use the 125,000 over 27 that 6 over 100 to the negative third actually is. You can also do that longhand and it would work out nicely. It's just easier to use that number because if I do, when I take the cube root of it, I get 50 over 3. And that's nice. I'm almost ready. Price is 125,000 over 50 divided by 3. I could use a calculator at this point, but I know I can multiply both by, if I have 125,000 over 50 over 3, I can multiply by the reciprocal 3/50ths, and I get $7,500. That is the price that will maximize my profits. The number of units that will maximize profits, that's what I got before, the 4629.63, and I'll maximize profits. And that all came from, finding the derivative, or finding profit so I could take the derivative of it, and then setting it equal to 0. Got the x, which is units, and then I use the x to tell me what the price is that maximizes our profits overall. That's on 11. Tough problem. Hope that helps you along.